it's still fair.
Okay.
This is almost
Okay. Hi everyone. Hi. Okay, that's good. So let's start. Last time we finished the preliminaries and then we talked about the local search and its variants. For example, local search, guided local search, iterative local search, and also the BNS and GNS. And so afterwards we talked about Boltzmann distribution, but let me go through the Boltzmann distribution very fast again, just to recap. So as we saw, Boltzmann distribution, also called Gibbs distribution, was initially proposed in 1868 and then in 1902. So we talked about the energy-based distribution. So it's the energy-based distribution. Whenever we hear energy, we should think of physics. And so it is used to describe the physical systems stochastically. So we said that in we see that in quantum mechanics, in particle physics, also in high energy physics, right? For example, one of the models is the Ising model, and we said that there are some particles. Particles in physics, they usually rotate. So an example particle is electron, right? So they usually rotate either clockwise or counterclockwise. Based on whether they rotate clockwise or counterclockwise, then we have positive or negative spins. Therefore, assume we have d particles, and you can see these d particles, each of which has some state +1 or -1, based on whether, depending on whether it's rotating clockwise or counterclockwise. And if you consider these d particles together, you can see it as a vector, a binary vector, right? A d-dimensional binary vector. And then we said the Boltzmann distribution, what does it do? It shows the probability that a physical system can have a specific state. So we can have different permutations of +1 and -1 for the particles. So such as 1, 1, -1, -1, 1, or some other permutations. Then the probability mass function of the Boltzmann distribution is shown in equation 1. This is the probability that a bunch of particles next to each other can have a specific state, right? So this x here shows a specific permutation of +1, -1. And E of x is the energy of the variable x, right? And z is a normalization constant. Do you remember? I talked to you about why we need normalization constant. How can I hide this one? Okay, that's fine. So how can do you remember? I said we have a bunch of numbers. How can we make them behave like a probability? So I asked you guys and you answered. So we can simply divide them by the summation of all of them. In this way, they will become, all of them become between 0 and 1. Of course, I'm assuming they are non-negative. They will be between 0 and 1, and then also they will sum to 1. So they behave like a probability. What I said, what if I want the probability to be like a Gaussian distribution? or a normal distribution. Then we said, okay, let's bring x to the power of exponential operator. So we have e to the power of x. In this case, it becomes like a Gaussian distribution. Why? Because the Gaussian distribution has exponential operator in it, and we have a family of distributions which have exponential operator in them. And Gaussian distribution is one of them. But another problem arises, and that was e to the power of x. It doesn't sum to 1. Also, it's not necessarily between 0 and 1. So what should we do? We should divide it by the summation of all e to the x's, right? And then we said in machine learning, they call this softmax form. Right? But there is a problem with this technique, either x to the summation of x or e to the power of x over summation of e to the power of x. What is the problem with that? Can you tell me? In this expression that we have, there is a pain in the neck thing. And what is that? Assume you are a computer program, and you want to calculate this. What will be the hardest part for you to calculate in this expression? Yeah. Yeah, the summation in the denominator is a pain in the neck, especially if the number of points here, d, for example, whatever, is huge, right? Or all different permutations is huge. Then the summation blows up. Then the time complexity is up for calculating. Although the time complexity is linear, but what if your the number of states is, or the number of possible permutations is too big? Then you will it will take forever to calculate this summation, right? So that is a problem of this technique. So softmax form has this issue. And normalization in Z here is a normalization factor, which makes this probability between 0 and 1 also makes it to sum to 1. And as you see in equation 2, it is summing over all permutations of the x's, of the dx's, right? And you can imagine, assume you have 2 x's, these 2. Then how many cases do you have? 4, right? 0, 0, 0, 1, 1, 0, 1, 1. What if you have 3? 2 to the power of 3 cases, 8. What if you have 10 particles? You have 2 to the power of 10, 1024 cases. So it's, as you see, it's exponential growth. Okay, so that's weird. So, but I can tell you, although it's out of the scope of this course, there is a technique to calculate this normalization factor, also called partition function. There is a technique for that. And for interested students, you can look up factor graphs. Yes. Sorry, what? Function of the energy, because as we said also, every permutation of the particles has some energy, and we want the energy to stabilize. That's the reason. So every permutation that you can it has some energy, and that's the reason. So based on the energy, we can find out whether the probability is high or low, whether the energy has stabilized or not. That is the reason that the probability has energy in it. So, I was saying that calculation of Z is hard, but there are techniques for calculating it efficiently. And one technique is in factor graphs. Just search it and you'll find out. So we have factor graphs, also normal graphs. And so factor graphs simply are some fun. So they get some variables. There are some functions and they get some variables. Again, so you can have combination of functions and variables. We see similar thing to the factor graph today, hopefully, and that is in genetic programming. Okay. But anyway, yeah, in factor graphs, there are techniques to calculate this Z efficiently. I don't know if you have heard of forward-backward propagation. Have you heard of it? So if you have seen hidden Markov models, and so they use forward-backward propagation. So all of these are related to each other. Local graphs, sorry, normal graphs, factor graphs, forward-backward propagation, Markov models, hidden Markov models. And in those, there are techniques to calculate Z efficiently. Basically, to give you a rough idea how they do that, assume there are particles, right, connected to each other. So you can have maybe two sides of this, assume it is mesh or whatever. You can have one side, one starting side and one end side of this mesh, for example. You start from the starting node, you propagate, and also you start backward from the end and you propagate. So you will have forward and backward propagation, and there are techniques using this forward and backward propagation, we can calculate Z. Anyway, that's out of the scope of this course. You can take a look at that offline. But I was saying that Z is a problem. However, here, in our algorithm at least, we don't care about Z much. We'll see. Okay. So here, as I said, the probability Boltzmann distribution is this. And by the way, the Boltzmann distribution has other use cases in machine learning too. Again, I want to trigger your minds to go and search up down, although these are not related to the course one, but Boltzmann distribution is also used in Boltzmann machines or restricted Boltzmann machines. Have you heard of the restricted Boltzmann machine or RBM? No. RBMs are one of the fundamental neural networks, especially in deep learning. Before deep learning could become deep learning, it was neural networks, right? They couldn't make it deep, and it was losing the competition against support vector machine. Then, I don't know if you have heard of Geoffrey Hinton. Have you heard of him? Geoffrey Hinton is one of the godfathers of AI. He has retired. He was a professor in University of Toronto. So what did he do? He was one of the founders of backpropagation algorithm for deep neural networks. And then he figured out that we are facing a winter for neural networks. We can't make the neural network deep. And at that time, it was around 2000 to 2006. At that time, he said he suddenly remembered his old algorithm named restricted Boltzmann machine or Boltzmann machine. And then he figured out that every layer of neural network can be considered as a restricted Boltzmann machine. And using that, he published an important paper in 2006 saying that we can make neural network deep if we initialize the weights of neural network using RBM training or restricted Boltzmann machine training. And afterwards, nowadays, why haven't you heard of RBM? Because around 2011-12, two techniques came up, which were dropout and ReLU. And people figured out that if they use dropout and ReLU in deep learning, they don't need to initialize the weights anymore by RBM. They can initialize them randomly, and still they can get deep in neural network. That's why nowadays, maybe you haven't heard of RBM. But if you watch or listen to any of the speeches by Hinton loves RBM. He's kind of obsessed with RBM. And if you have seen, I can say all of his speeches, he talks about RBM because he strongly believed in RBM. It was like his child. So, by the way, what is RBM? Consider this. Three nodes or neurons, whatever, at top, and four neurons at bottom. Assume they are connected to each other. Okay. Also, the neurons here are also connected to each other. Okay. This layer has some energy. We can define some energy for it. This energy is also called belief. Also, this layer has some energy or belief in it. Then I can go back and forth between these, saying that I want to copy the information or the belief or the energy of one layer to another layer, back and forth. Of course, if the number of neurons were the same or the number of nodes were the same, the copy would be the exact copy, right? You exactly copy the values of these neurons to the next neurons because the number of neurons would be the same. However, the problem here is that we have 3 neurons top and 4 neurons in the bottom. So you need to preserve the information, but the number of neurons change. Okay. So and this is Boltzmann machine, by the way. Can I say that one layer of neural network is just a stack of layers? If you haven't seen neural networks, for example, this is a neural network. The neurons of each layer are connected to the neurons of the next layer. Okay. Can you see that every layer of neural network is like a Boltzmann machine? But there is a difference. What is the difference? In neural network, the neurons of the same layer are not connected to each other, right? For example, here, this neuron is not connected to this neuron, right? So Hinton removed these connections, which are the connections between the neurons in the same layer. That's why he called it restricted Boltzmann machine, because he restricted the connections. In short, RBM. As a result, every layer of neural network can be seen as a restricted Boltzmann machine. Anyway, I said these in parentheses to tell you that for RBM training, we use Boltzmann distribution. The RBM's name comes from the Boltzmann distribution, right? Boltzmann machine. Okay, so it has use cases a lot in different fields of science, in physics, in machine learning, here in materialistic optimization. So where were we? Okay, this was the Boltzmann distribution. We have coefficient beta, which is greater than or equal to 0. And beta, according to physics, is 1 over k beta T. And T here is the absolute thermodynamic temperature in kelvins. It's not in Celsius, it's absolute temperature. It's in kelvins and it's non-negative, so it can't get negative. It's always 0 or positive. And therefore, beta is proportional to 1 over T. Here, K beta is the Boltzmann constant. We can ignore it. For R, in physics, you can't ignore it. Here, we are using this in our algorithm, so we can set it to 1. We can ignore it, right? Because we're doing computer programming. In physics, you shouldn't do that. Okay. If the temperature goes to 0, the T goes to 0, then according to equation 3, beta goes to infinity, right? And if beta goes to infinity in the Boltzmann distribution, e to the minus beta x goes to 0. So it means that when T goes to 0, the probability also goes to 0. It means that in the universe, the probability that we have 0 temperature in terms of kelvins is very rare, maybe between galaxies. Okay, let me go faster on these. So this was the Boltzmann distribution and the partition function. The free energy we said is defined as this, and also the internal energy is this, and we showed that we can simplify the internal energy as done in equation 6. And here I'm putting the equations all together, and also then we define the entropy, and we could write the entropy based on as a function of free energy and internal energy as done in equation 7, right? Okay, then we talked about the fact that a physical system prefers to be in low energy. So answering your question, saying that why do we need energy in our probability? Because the physical system tends to have low energy. Therefore, the lower the energy, the higher the probability, right? And hence the system always loses energy to have less energy. And for that, for the proof of that, we use the second law of thermodynamics, which says the entropy of a physical system always increases by passing time. And we had a corollary or a conclusion saying that according to that equation, according to the Boltzmann distribution, when the energy goes down, the probability goes up as expected because the energy of the system tends to go down, right? And also, we said that so the systems tend to become more probable because the systems tend to lose energy, therefore they tend to become more probable. And this idea is used in simulated annealing. Okay, so by the way, then you know what is annealing in physics? So when you have a very hot material and you cool it down gradually, they call it annealing. For example, so you can see it either in high energy physics, so it has a lot of energy, or you can see it in when they want to make art glasses. So you have some melt glass and you pull it down to become some dish or something like that. So you can see that as also annealing process. The temperature of the system is cooled down gradually in annealing. And why do they call it simulated annealing? Because we are simulating it in our computer program. So it's a meta-heuristic optimization, simulated annealing, and it has a temperature parameter which controls the amount of global search versus local search. Okay, so what does it do? It reduces the temperature gradually to decrease the exploration. Why? When initially my temperature is high, okay, so I can search a lot in different places of the landscape, optimization landscape. Therefore, it's good for exploration. Okay, gradually I cool it down according to annealing. Right? I anneal that, so I cool down the temperature. By cooling down the temperature, we'll have more local search rather than jumping to the different parts of the landscape. Therefore, by cooling down, we increase exploitation. And as I said several times, usually in materialistic optimization, we first explore and then we gradually exploit, right? We also see that in deep learning. Initially, we have larger learning rates. So we jump with the larger steps in gradient descent, and then we gradually decrease the learning rate to exploit more. And I think the philosophy is understandable because the more we go in the algorithm, the closer we assume we are to the actual solution. So we should search there more rather than exploring. We shouldn't jump around the solution. We should be around the solution with fine steps. Okay. So yeah, and as I said, we assume beta is 1/t. So because it's not physics, we are using that in our program, so I assume k beta is 1. And then equation 10, we have so the Boltzmann distribution becomes e to the power minus ex/t. And we also have z in the denominator. So ex is the energy, t is the Kelvin temperature, and z is the normalization constant or partition function. Now I have E of x energy, right? So I can replace it with delta E. Right? Energy, I can replace it with the difference of energies. Assume I'm comparing two energies. Okay. The delta E is the difference of two energies. And so let's see. Now let's go into the simulated annealing algorithm. So far, it was the preliminaries of simulated annealing. So the idea was proposed in 1983. As you see, it's an old algorithm, and it is inspired by the annealing schedule in high energy physics for forming the shape of materials, like glass. It is used in various applications such as VLSI short for very large scale integration, and also circuit routing. Is anyone from electrical engineering here? Yeah, so are you familiar with VLSI? No? So VLSI is have you seen ICs? Right? Integrated circuits. So our computers, motherboards, there are a lot of ICs there, right? So if you zoom into the IC circuits, you can see some pattern like this. So these are just wires between different things, right? But they're very tiny. But we need to optimize these. Why? Because, for example, from this point to this point, there are a lot of paths. But the paths should not intersect each other. Sometimes we have to, for example, there is no choice. I have this, and there is no choice. So sometimes there is choice to like this. Sometimes I can't. When I can't, then I do this. Okay. Then I can connect these with a device, another device outside. So what do I mean? So there are a lot of tiny devices, right? Tiny like capacitors, tiny things which we put on this board. This board, by the way, is also called PCB board. I think P stands for printable something. But PCB boards, they have a lot of wires on them. You put the different electrical devices such as capacitors, resistors, and these things on them, and then they are connected to each other. So as I said, for connections, either we can do this or we have to use external devices. But anyways, we have to optimize these paths, right? You can see that the routing problem. And you can set the same algorithm that is used, for example, for this routing. You can use this with some changes. We can use that for routing in Amazon robots. So, for example, there are robots in Amazon that they want to route and find the product and bring it to the shipping center or something like that. So they also route, find the best routes. Also here, we are finding the best routes for the paths on the PCB. And yeah, as I said, we need to optimize them. And in VLSI, it's very large scale integration used for IC production and also circuit routing. By the way, if it is not too tiny IC, so if it is too tiny IC, they use HSIC for that. If it is not too tiny, so you can design it yourself. For example, it's a big board, but you can design it yourself. You can use there are various applications for that. I think one of them was Altium Designer, as far as I remember. Another one was Proteus RS. Yeah, good time, good memories. I remember I had to design these PCB boards sometime in my life. Okay, anyways, so it's used for designing these boards. So step one, choose some initial candidates, right? Some candidate solutions. And initial temperature. So we use some initial candidate. I think it should be singular, not plural. And then in every iteration, do a local search in a neighborhood of candidates or candidate, doesn't matter, and choose a neighbor point for every candidate. For simplicity, assume I have one candidate for now. We can extend it to several candidates. So assume I have a candidate solution, somewhere in optimization density. Then what can we do? I do a local search, okay? A local search, assume, usually in simulated annealing, I don't search for different neighboring points, only one neighboring point. And then Assume I see one of my neighboring points. I evaluate its fitness or cost, and then I calculate the difference of their costs, okay? Here, I assume my cost is like energy, right? In simulated annealing, I assume cost is the energy. Or the delta E is the difference of cost or difference of energy. So I calculate delta E, and what is delta E? Delta E is the cost of neighbor minus cost of it's the point, the candidate, okay? Do you agree that if delta E becomes less than 0, is it better or is it worse? If delta E becomes less than 0, what happens? What does it mean? It means that the cost of neighbor is less than the cost of myself. Am I right? So delta E is the cost of neighbor minus my cost. If delta E is negative, it means that the cost of neighbor is less. So the neighbor is better than me because its cost is less than me. Therefore, I accept it with probability 1. I definitely accept it, right? Because it's better. But what if my delta E is greater than 0? So the cost of neighbor is more than my cost. Should I accept it or should I reject it? In initial glance, you might say, reject it, right? But there is a philosophical question here. Should we reject all worse candidates? If I reject all worse candidates, what happens? I will get stuck in where I am. I will get stuck in the local best. I will only exploit. For exploration, I should allow some worse candidates, right? Otherwise, I will not get out of where I am, right? It's like in real world. So you should also listen to others, even if you think they are wrong, right? What if by listening to them, you find out that later that you were wrong, right? If you don't listen to others, you will always get stuck in where you were, right? Exactly here. So the main idea, the important algorithms in materialistic optimization, each of them has some main idea. The main idea of simulated annealing is giving a chance to worse candidates. Okay? Let's give a chance to worse candidates. So, but should I definitely accept the worst candidates? If I do that, that will also be awful. Why? Because I will always jump. I will always explore. I will never exploit. Right? Therefore, I should probably accept the worst candidates. Probably. With some probability. What probability? Simulated annealing uses Boltzmann distribution for them. Okay? And why does it use Boltzmann distribution? So whenever you want to understand an algorithm, put yourself in the shoes of the designers of the algorithm. Assume you were saying that, okay, the philosophy of my algorithm is to give a chance to worse candidates. But what probability should I use? I should use a probability which changes over time, right? And initially, I should give more chance to worse candidates. Later, I should give less chance to worse candidates because initially, I want to explore more. Later, I want to exploit more. So what probability can I use? Maybe Boltzmann distribution, right? So Boltzmann distribution is this. What is its parameter? Temperature T. Okay, I want initially this probability to be large. For this to be large, the power is e to the minus delta E over T. Therefore, for this e to the power minus delta E over T should be large. The power also should be large. So minus delta E over T should be large. Therefore, delta E over T should be low. Therefore, T should be large. Let me repeat. E to the minus delta E over T should be large initially. Therefore, minus delta E over T should be large. Therefore, delta E over T should be low. Therefore, T should be large. Agreed? So initially is this. Later that I want this probability to be low, it should be the other way around. E to the power minus delta E over T should be low. So minus delta E over T should be low. So delta E over T should be high, large. So T should be low. Agree? As a result, initially T should be large. Gradually T should decrease. Okay. So this gives a chance, as I said, to even worse candidates for exploration, not to get stuck in local optimum. And therefore, as I said, we need to decrease T. So we gradually increase exploitation and decrease exploration. So how can we decrease a parameter? Is in different ways, right? Any way to decrease the parameter gives you a variant of simulated annealing. So example, we can have linear reduction rule where we say T equals the previous T minus some alpha, some constant, right? Agreed? This T, by the way, shouldn't get negative, right? We should be careful when we are decreasing that. We should be careful. It shouldn't become negative. Otherwise, this minus becomes positive and everything becomes bad. Agreed? Okay. Now, because for this analysis to hold, we need to have this minus. Okay. Also, we can decrease it geometrically. So we can multiply it by some alpha between 0 and 1, right? Also, we can have a slow decrease rule. Why? Because these two decrease with high rates. Even if, unless for this not to decrease too much, alpha should be very small. For this, alpha should be close to 1. But if you want to have a slow decrease, you can use this T is the previous T over 1 plus beta previous T, where beta is a hyperparameter, positive. Sorry. Okay, where beta is the hyperparameter. Okay. Now this is the algorithm for simulated annealing. So we initialize the solution X, right? And while not converged, so we have iterations, right? In meteoristic optimization, we usually have iterations. We are optimizing iteratively. Then get a point from the neighborhood, right? Get some point from the neighborhood and evaluate its fitness or cost function and calculate delta E. Okay. In the simulated annealing, if you want to use this algorithm, if this equation 12, you should use cost. If you are using fitness, I think you know what you should do, right? If you are using fitness, you are maximizing a fitness, right? If you are maximizing a fitness, what change should you apply? Either you multiply the fitness by -1 to become cost, or you change the order in delta E. If you set delta E to be fitness of point minus fitness of neighbor, then again, negative delta E would be accepted. And positive delta E, you should give a chance to them. Do you agree? Did you understand what I'm saying? That I'm saying that you should be careful that here delta E is negative means that my neighbor is better. My neighbor is better. If you are minimizing a cost, then delta E is this equation. If you are maximizing a fitness, delta E should be fitness of point minus fitness of neighbor. Agreed? Okay. So again, if delta E is negative, it means that my neighbor is better than me. Absolutely. Okay. Either in terms of cost or fitness, whatever. Then I update my solution to that neighbor because that's better than me. And I break the loop. So I go, no, sorry, I shouldn't break the loop. I apologize. I will correct this. You shouldn't break this. I go to the next iteration. Okay, I update myself. Otherwise, what should I do? Otherwise, I should accept it with some probability, right? But in computer, how can I say accept it? For example, I calculate in equation 12, assume I calculate this. Delta E is a number, right? Is a float number. T is some number. E to the power minus delta E over T will be some number between 0 and 1. Do you agree? Do you agree with that? First off, that's the reason I got rid of Z. Why didn't you ask me where did Z go? Did you notice that in equation 12, I'm not using Z? Yes, I said it's not important, but do you agree that the probability must be between 0 and 1? But I tell you that this is between 0 and 1. It doesn't sum to 1. I don't care here. But it is between 0 and 1. Because e to the power minus something, if that thing is always positive, it's always between 0 and 1. Don't you agree? Okay, that's the reason. So Z is not, if it wouldn't become between 0 and 1, I had to make it between 0 and 1 because I'm using that as a probability. So you might be wondering, why did we use Z in physics in the first place? Because it doesn't sum to 1. Here, I don't care whether it sums to 1 or not, because I'm only considering 1 point. I give some probability to it. Understand? You understand what I'm saying? Okay. Anyways, assume I calculate this probability, assume it becomes 0.7. Then how can I accept the worst, this worst neighbor with probability 0.7 in computer? In English, I will tell you accept it with probability 0.7. How do you code it? Yes. Sorry, what? We put it in array? No, it's a scalar. It's a scalar probability 0.7, and I want to whether accept with this probability or not. How can I do that? Almost correct. So we generate a random value between 0 and 1. We can do that. In any programming language you are using, you can generate a random value between 0 and 1. Do you agree? In Python, in MATLAB, in C, whatever, generate some random number between 0 and 1 and compare that random number with this value. If it is less than this value, accept. So it means that accept it. Otherwise, if it's greater than this value, reject it. Don't you agree?
Does it matter what distribution? Like,
yes, it matters. You should generate a random value from uniform. Uniform random value between 0 and 1. Okay. Did you understand how to use probability in programming language? Generate a uniform number between 0 and 1 and compare it to the probability. And so this is exactly what I'm doing here. Generating a uniform random value. If it is less than the probability, accept that neighbor and update the solution. Otherwise, reject it and stay where you were. Yes? For all comparisons, what do you mean? Yes, but this probability changes, right? So why does this probability change, by the way? Because in every iteration, so because we have worst point, we have very worst point, we have very, very worst point, you can't see all of the worst points with the same eye. Okay, assume this is my cost. I'm here now. This is also a neighbor. This is also a neighbor. This is also a neighbor. All of them are worse. But this is worse than all of them. This is the worst one. I shouldn't see all of them with the same eye. I should give more chance to this, less chance to this, and much less chance to this. Agreed? this probability, the probability of acceptance decreases if the cost of the neighbor is higher. The more the cost of the neighbor, the less the probability of acceptance. I told you this algorithm gives a chance to worse points, but doesn't see all of the worst points with the same eye. It gives more chance to the worst points if they are better. Yes?
It seems pretty inefficient if you're jumping like to a worse neighbor and you're like with a very high chance of hitting the worst.
So you're saying that it's inefficient. I say no. Why? Because we're doing that in initial iterations. In initial iterations, we jump a lot because this probability is usually large, right? This probability is usually large. But the more we go, this probability goes down. This probability goes down. So later, we don't jump much. In other words, let me tell you one thing. This probability is minus e to the minus delta E over t, right? How does this probability go down? In two ways. Either t is decreased or delta E is increased. The more we go in the algorithm, the less the temperature comes, so this probability goes down. Also, at every iteration, I calculate my delta E. If my neighbor is much worse than me, again, this probability goes down, even if t is large. Do you understand the effect of these two? So initially, it jumps a lot. Gradually, it doesn't jump much to exploit. Okay, this is the, and I think this is the analysis. I explained this a lot. So this is the curve, the plot of e to the minus 1 over t with respect to t. And as you see, it's between 0 and 1. The more you increase temperature, the more this probability. In the algorithm, we go in this way. We decrease the temperature. So initially, the temperature is high, the probability is high, we have more exploration. Gradually, we have more exploitation. Okay, again, as I said, it's very similar to what we do in gradient descent and backpropagation. Initially, we have a high learning rate and we decrease the learning rate gradually. But someone might say, I'm very lazy, or it's hard for my computer programming to calculate the Boltzmann distribution, right? Someone might say that. For example, I don't know, your manager says we don't have enough space in our embedded system, or we don't have enough resources for you to calculate this Boltzmann distribution, or you are optimizing something for NASA, and NASA doesn't have enough time for you, even in milliseconds, to calculate this Boltzmann distribution. In these cases, you can modify equation 12 to this. So you can calculate delta E and compare it with some threshold. Okay. If it is less than that, because we know that delta E, if it is negative, I should definitely accept that. If it is positive, I should probably accept that. Therefore, I can compare delta E with some positive number. If it is less than this positive number, I accept it. So if it is if delta E is negative, I definitely accept it. If it is positive but less than Q, I still accept that. But if it is greater than Q, I reject it. But this Q itself should have the idea of cooling down the temperature. So the Q itself is a decreasing function with respect to iteration index. So initially, when Q is large, I give more chance to worse point. Gradually, I decrease Q. So I give less chance to the worst points. And Q is greater than or equal to 0. So Q never gets negative. So it's called threshold accepting. Acknowledgement, some slides of this slide deck are inspired by teachings of Professor Said Sharifian at Amir Kabir University of Technology, Department of Electrical Engineering. Also, some slides of this slide deck, especially the Boltzmann distribution and statistical physics, are inspired by teachings of Professor Mehdi Molkarai here at the University of Waterloo Department of Statistics. He has a very good course. It's graduate course. Called, I think it's about Markov chain Monte Carlos, and also he talks about statistical physics. This slide deck is also based on our some parts, especially the Boltzmann distribution. For that, you can refer to our tutorial paper, Restricted Boltzmann Machine and Deep Leaf Network Tutorial and Survey. Okay, these are the references. By the way, I don't know if I told you or not. So I said the Boltzmann distribution is related to Boltzmann machine, restricted Boltzmann machine, statistical physics, factor graphs. You can also relate it to Hopfield networks. I don't know if you have heard of that or not. Hopfield network is a neural network which tries to model memory, how our memory works. Okay, so it's very interesting. Hopfield. Okay, I heard that Hopfield was gonna get Nobel Prize for that, but he didn't, I guess. Okay. So, let's go to PSO. Okay. The next meteoristic optimization algorithm that we have. By the way, any question so far? Yeah.
When you did the graph and you said that, oh, I should give, this is a worse solution and this one is even worse,
Okay.
then you'll give it less chance.
Yeah.
You'll give it less chance because at that point you move 2 times and the temperature is lower, so you give it less chance.
Can you repeat?
Yeah, it's okay.
No. So let me explain the simulated annealing more. I think it. Yes.
Way the algorithm gives less chance to the worst solution.
Yes.
It's because going further, it still grows worse. And the only way the algorithm gives it less chance is because you went through multiple iterations at that point.
Yes. So I think if I explain in this way, it will also answer your question and it also clarifies for everyone. So that probability of accepting worst point was e to the power minus delta E over t. Agreed? Initial iterations. T is large. Okay. And later, T goes down. So we have 4 cases. Delta E, so T large, delta E large, T large, delta E low, small, T, by the way, when I say low, I mean still positive. Delta E is here, I assume is positive because it's worst point. T small, let's call it small. Delta E large, T is small, delta E is small. We have these 4 cases, right? Let's analyze 4 cases. When is T large? So in these 2 cases, what does it mean that T is large? I'm in initial iterations, right? I'm at the start of the algorithm, initial iteration. The start of algorithm. These 2, as T is small, I'm almost at the end of the algorithm. Now let's go to the subcases. So here, when delta E is large, what does it mean? Yeah, the neighbor is very bad, very worse, right? So neighbor, very worse. So what does it mean? For example, my cost is 1, the cost of neighbor is 100, right? And delta E is a small, means neighbor's cost close to mine. Agreed? Also here, delta E is large, means neighbor, very worse. Delta E is small, means neighbors, cost, close to mine. So the first subcase, it's a start of algorithm. The neighbor is very bad. The second subcase, start of algorithm, the neighbor is worse than me, but not very bad. The third subcase, almost at the end of the algorithm, the neighbor is very, very bad. The fourth one is almost the end of the algorithm. The neighbor is worse than me, but close to my cost. For example, my cost is 1, neighbor's cost is 1.5. Okay, so now you tell me, in these cases, what happens to the probability? When T is large, delta E is also large. What happened? When this one, when T is large, delta E is small. P is large. Agreed? This one, P is almost small. I can say almost. Okay? The third subcase, T is small, delta E is large. T is small. So what happens? Let me think. T is small, so the fraction is large. The numerator is fraction is also large, so the whole fraction is large. The whole fraction, so P is small, right? P is small. This one, P is, I believe P is still small, but this is, I can say too small. This is also too small, but this is much too small. So if I want to compare this is very small probability. The third subcase. The first subcase is small, very small. So very small, almost. So this is almost small. This is large. Let's analyze it. Of course, when in the initial iterations, let's start with the end of. In the end of the algorithm, what happens in the end of algorithm? If my neighbor is much worse, of course I shouldn't accept that. The probability is very too small, because if the cost of neighbor is awful, the temperature is also small. Two awful things make the probability very awful, right? So this is the case. Here, I'm at the end of the algorithm, but my neighbor's cost is a bit worse than me. But still, my probability is low because I'm at the end of the algorithm. As I said, at the end, I usually exploit. I don't explore much. Here, I'm at the start of the algorithm. T is large, and my neighbor is good almost. A bit worse than me. Of course, the probability is high, maybe close to 1.9 something. Here, I'm at the start of the algorithm, but my neighbor is very worse. So still, the probability is low. Did you understand completely how the simulated annealing is working using these 4 subcases? Okay. So the next thing is PSO, particle swarm optimization. One of the most interesting materialistic optimization algorithms. So usually some of the materialistic optimization algorithms were breakthroughs, and they impacted all other algorithms afterwards. One of them was PSO. So nowadays, when you see many of the algorithms, they have the idea in the backbone of PSO. Okay. Particle swarm optimization. So first, swarm optimization, the idea. By the way, this swarm optimization is a field itself. It has journal for swarm optimization something. I think Elsevier has swarm intelligence journal. So what does it do? some of the materialistic optimization algorithms are swarm optimization methods, also called swarm intelligence. In swarm methods, we have a swarm of particles. What do I mean by swarm of particles? A group of particles, a team of particles, or when there are a flock of particles, like a flock of birds. So we have a swarm of particles with which collaboratively try to find the global best in an optimization landscape. Okay. So far, so in local search, in simulated annealing, we didn't have several particles collaborating. It was one particle searching. Agreed? So far, we had only one particle searching its around and updating itself. PSO was the first algorithm which said, why do I need only one? Let me have several particles which collaborate with each other. Okay. So the swarm methods are usually, but not always, bio-inspired or nature-inspired algorithms where the particles behave like animals, birds, creatures, etc. Okay. By the way, now you understand why the title of the course has cooperative algorithms. So they are cooperating, right? These particles. This is one of the algorithms for cooperative algorithms. So, and as I said, they are bio-inspired and or nature-inspired. So that's also a field. A subfield of swarm intelligence is nature-inspired optimization. They have found, so that has become very crazy. They have searched that whatever creature we have in the world that they haven't yet proposed an algorithm, let's propose an algorithm for that. This is how they publish papers. So let's find some creature in the sea or in the jungle and propose an algorithm for them. Okay. So a recent survey on the nature-inspired optimization is published recently. If you take a look at this paper, you can see that there are algorithms from the bottom of the ocean until above in the sky. All of the creatures in these areas are published. Okay. For example, a swarm method. By the way, what do I mean by nature-inspired? For example, they find whale. Okay. We want to propose an algorithm for whale. They don't say, okay, let's propose an algorithm and call it whale. No, it's the other way around. They go to the whale, they see its behavior, they try to design their algorithm to imitate the behavior of whale. Right? Do you understand what I'm saying? Or for example, gray wolf optimizer. What does it do? It looks at how gray wolves in the poles, assume there is a mammoth, right? Am I pronouncing it correct? Mammoth or elephant. There's an elephant or ancient elephant, mammoth, in pole. There are gray wolves which want to attack it and eat it. Okay. Of course, one gray wolf cannot attack a big elephant. A big elephant can defeat against that one gray wolf. So they come with a team. They are a swarm of gray wolves. And how do they attack? Have you seen? They attack from different directions of the elephant. So the elephant can see it's the front. But they want to confuse the elephant. So they make a circle around it. And then they jump from its back. And also, so this is now if you go and see the gray wolf optimizer, there are some particles which surround some solution or some part of the landscape. So, do you understand? And attacking, for example, they say let's call the local search attacking. Do you understand what I'm saying? So this is how nature-inspired algorithms are. Okay. Many bio-inspired or swarm materialistic algorithms exist, many of them, such as particle swarm optimization or PSO in short. It was proposed in 1995. Ant colony, we will cover it hopefully, in 1996. So ant colony imitates the behavior of ants in a colony or a swarm of ants. That's actually, don't think that these are very naive algorithms. Ant colony can be used for graph optimization a lot. because imagine a graph with lines between the vertices, with edges between the vertices. Now assume you have a bunch of ants walking on the edges of the graph. So you use an ant colony, you can find the shortest path, because the ants try to find the shortest path. We'll cover it. We'll cover it. It's very interesting. Okay. So again, assume you have a graph and you put a bunch of ants on it, and they are walking on this graph along the edges. Okay. We have Gray Wolf optimizer proposed in 2014. So it's one of the state-of-the-art algorithms, actually. If you see its citation, it will blow up your mind. I think more than 10,000 citations, I believe. I am not sure. Or close to that. So whale optimization algorithm, 2016. SALP swarm algorithm, 2017. SALP is in the ocean, right? Also a scholar in this area is Said Ali Mirjalili. He's a professor currently. When I was studying master's, he was a PhD student in Australia. Now he is a full professor in Australia. So in Torrens University, Australia, you can see his Google Scholar page, and you can see a lot of nature-inspired algorithms in his publications, such as Gray Wolf optimizer. Okay, now PSO, the idea of PSO, proposed in 1995. So what is it? Do you remember? This is the idea that initially I mentioned for introducing the materialistic optimization to you in preliminaries. So let me repeat it briefly again. Assume I have some treasure in the ground of this room, okay? Somewhere, but I don't know where. We are a bunch of people, a bunch of friends, a swarm of friends, a swarm of humans. And so each of us is like a particle. Then what do? We say, okay, randomly, each of us selects some region in this room, okay? And so this is random initialization, okay? Then each of us digs that region specific to that person. So when I say dig, what do I mean? Local search, I mean, right? When I say dig, I mean dig and see whether you can find a treasure or not. So local search, okay? And then what do I do? By the way, although these algorithms might seem naive, but they're very powerful, very powerful. You have no idea how you can use them in industry also. So anyway, you dig, you find some solution. I, for example, find plastic as my best finding. You find some gold, and you find some, assume you are three. I find plastic in this situation, you find gold, you find some diamond. Okay, then we announce our findings, and of course the diamond is the global best, but the worst is the plastic, and the nil case scenario is gold, for example. So you, me, and you, we move toward that the global best, because apparently the treasure must be around there. But we don't go exactly there. Why? Because that person is already there. He or she will search there, right? They will search there themselves. We don't need to go there exactly. Let's move toward that person. Why? Because in the middle of the way, maybe we find a better solution. Okay. So I move a little bit toward that global best, but also toward my local best. For example, my local best was plastic. So therefore I have vectors. I have a linear combination of these vectors. I move a little bit with some step. You also do that. That person does a local search, keeps search there. We search in the second iteration. Then suddenly I say, oh, by the way, I found two diamonds in the middle. Although I had found plastic, but in this iteration I found two diamonds. If this case happens, what does it mean? It means that this optimization landscape is too complicated. If in this iteration I found garbage, the next iteration a little bit in some neighborhood around that, I found the global best. It means that the optimization landscape is highly non-linear, highly non-convex. Okay. So I found 2 diamonds. You, that person found gold. You found plastic this time. Then the global best is updated here. So those 2 people now move toward me, and I keep searching them. We do this iteratively until gradually we converge to collaboratively, we converge to the global base, right? Understood? That's called particle swarm optimization. So as I said, it's bio-inspired. Why? Because it is inspired by a flock of birds or a group of fish. Okay. And swarm optimization. Okay. So this was the idea. Now the formula. Okay. So the candidate solutions are particles or vectors. By the way, the particles can be vectors, can be matrices based on, depending on what is your optimization variable. If your optimization variable is a scalar, the particle is a scalar. If it is a vector, the particle is a vector. If it is a matrix, the particle is a matrix. So you have particles, and at each particle or at each variable, you can evaluate your fitness or cost function. Agree? Okay. Every particle searches locally. As you see, local search is the backbone of most of materialistic optimization algorithms, right? It searches locally in a local neighborhood. 3 components of the velocity vector for updating the solutions. So you can see these vectors that I move toward you as a velocity vector. Velocity vector, okay? So we have 3 things. First off, momentum or history of previous velocity for exploitation. What do I mean by this? Assume my vector, I denote it by VI. What do I mean by VI? The velocity for updating the particle Xi. So because I have several particles, assume I have particles X1, X2, X3. Xi is the ith particle. Vi is the vector of velocity for updating that particle. And what does Vik mean? The update vector for the ith particle in the kth iteration. The kth iteration, because it is an iterative algorithm, right? Now I want to calculate my Vi in this iteration, which is the k plus 1 iteration, the next iteration, right? So Vik plus 1, how do I calculate that? It has 3 terms. The first term is alpha 1 Vik. Alpha 1 and alpha 2 and alpha 3, these are some hyperparameter. Okay, some scalar hyperparameter. And alpha 1 Vik, it means that I want to have a memory of my previous update. Where have you seen this in optimization, in deep learning and these things? Where have you seen that? What? Marco? No, I haven't. That's fine. Say your guesses. What? But you can use it with backpropagation. But where do you use that? Have you seen that? So the ideas, by the way, are repeated a lot in science. So when you see some idea in this course, it doesn't mean that this is only for this course. You can use it in other fields. Yes, yeah. So we have SGD and Adam, for example, optimizers for deep learning, but also they have some option that you can use. And that option is momentum. Have you seen? Momentum. So momentum is exactly like this. So momentum, let me open a page. So assume Vk plus 1 equals Vk. What is gradient descent? In gradient descent, we have this. Do you agree? Plus delta V k plus 1 and delta V k plus 1. This is the update, right? In gradient descent is minus eta. Eta is a learning rate. Derivative of V with respect to your optimization variable. Assume X, W, whatever. Okay? This is exactly gradient descent. if you replace this delta V with this is gradient descent. This is, by the way, derivative, gradient. But gradient descent with momentum, what is that? It says rather than using this, use this. You see the difference? By the way, with some parameter, with some weight, alpha. Okay. What is this? It is using a log of previous memory. So this is the update in this iteration. This is the update in previous iteration. I want to have the impact of my previous update in my current update. I want to have some impact of it. In other words, I don't want to forget my previous update. How does it help in optimization of deep learning? Exactly, the step. So, for example, if you are, this is the cost, a complicated cost. If you do gradient descent, so by the way, you understand what do I mean by this, right? At each, so I'm looking at the cost from above, and at each line, the cost value is the same. So it's like a bowl or whatever you call it. Okay, so assume I start from here. If you do gradient descent, it might go like this. So it has a lot of oscillations. But if you do momentum, if you use this momentum, it will be smoother. It will have less oscillation. Momentum helps removing the oscillation, okay? Almost. So why does this happen? Because you are using the impact of previous updates, so it doesn't oscillate from the previous update much. Agreed? So as you see, the idea of momentum or log of previous history or whatever you call it is also used in PSO, in particle swarm optimization. Interesting. Yes. Here. Sorry, what can you mean? These are some weights or hyperparameters, some scalar values chosen by user. So we call it this learning rate in gradient descent. They call it this, I think, momentum rate or momentum parameter. By playing around with alpha and eta, you will get different behavior of convergence. Why? Because the more alpha you have, what happens? It means that the more you should give importance to the previous memory. The more eta, what does the more eta do? Exactly, the more exploration. Jump more. Right? Jump more. Understood? So, ask me if you have any question. Yeah.
Increasing over time, or is it like a...
No, the momentum doesn't keep increasing. Why do you say that? I disagree with that.
Hold on.
No, I don't think so. So you are always using a fraction of your previous memory in your updates. Okay. And by the way, these can be vectors, right? This is a vector. This is a vector. This is also a vector. No, I think it doesn't know. Okay, so we have a momentum term. Also, the second term, what is this? Can you tell me? X of local best of k minus xik. The third term, I will explain this to you, is the x of global best minus xik. Okay. And then, by the way, we use this to update the previous particle to be this ith particle in the next iteration. Now let's talk about the second and third terms. Okay, what? You have a question? Oh, so how can we pick the hyperparameters alpha 1, alpha 2, and alpha 3? either choose them randomly and see if they work well. But if it was here, we are not machine learning. If it was machine learning, I would say you should use validation set for choosing these hyperparameters. I don't know here, if you have a validation set, you can choose them. But usually I think people just choose them with some value, not too big, not too small. Maybe, for example, alpha. So they are usually between 0 and 1, and you play around with them depending on your choice. For example, you might say, what do they do? What these do? You should understand their meanings. It means how much should I give importance to my previous memory, or to my local best, or to my global best. Assume alpha 1 plus alpha 2 plus alpha 3 equals 1. Then you choose some values for them. It gives weights to these terms. Understood? Okay. There was another question here. Someone raised hand. No? Okay. So now let's talk about this. By the way, local best or global best? We have variants of PSO based on what is local best in this formula and what is global best. Okay. The local best. Do you agree that it can be the local best of the particle itself? In this iteration, for example, in this iteration, I've searched for several iterations. So it's a nested loop, a loop for iterations, and the inner loop for my local search, right? In my inner loop that I'm searching, maybe checking 10 neighbor points. One of them was plastic, one of them was mud, one of them was something. Among mud and plastic, which one is better? Plastic is better. My local best in this iteration was my plastic, right? When I announce it, what I found in this iteration, I say I found plastic. I don't say I found mud. Okay, so it can be the local best of particle itself in this iteration, or it can be the local best of particle itself so far, in all iterations so far. So far, in the first iteration, I found plastic. The next second iteration, I found, you tell me, copper, whatever. And then assume I never found, so far, I never found a better solution than copper. Then I said, my local best is copper. Do you see the difference of these two? This one is in my best finding. In this iteration, this is my best finding so far. Okay. Global best also can be interpreted in two ways. Global best of all iterations so far, it means best of best so far. Best of me, best of you, the best of us. I found copper, plastic, you found gold, copper, you found diamond, copper, plastic. The best is the diamond. Or it can be the best of solutions found by particle in this iteration. In this iteration, among the particles, what is the best find? Not so far. Do you see? Now, 2 times 2, at least you have 4 variants of PS. Agree? Okay. So let's see a figure for that to understand this better. So assume I have these 3 particles, x1, x2, x3. Okay. So these are the neighborhoods for my search in this iteration. Okay. Assume I found, so x1 found the best of x1 search here. Then x2 found the best of x2 here. And x3, its best is here. Here for local search in this figure, I'm using the best of particles in this iteration. Okay. And for global best, assume I'm using in this figure, I'm using the best of particles in this iteration. Okay. Assume, so among these 3, one of them is better, right? Assume this is the better. So I say this is global best. Okay. Now I want to find the velocity vector for updating x1. Let's see. So I should have a vector connecting x1 toward its local best. So x local minus x1 means the vector connecting x1 to x local. Sorry. Okay. So this is this term. Assume my previous velocity vector is this. But why have I started it from here? Because the vector, I don't care where it starts. It's just a direction and some value, right? Some length and some direction. I can move this velocity, but I want to update x1. So I should put its start in x1. I want to update x1. So here, maybe, for example, my previous x1 was here, and then, sorry, it was here, for example, and it came here. So this was velocity, but I'm moving this here. Okay, because as I said, I don't care where it was started. And then what is this? The vector for global. So x global minus x1, because this is a global. So the vector connecting x1 to x global. Now I have these three vectors. I can add them, right? But with what weight? Because here, toward the global best, I can come here, 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 here. Those alphas decide that. Those alpha values, right? Yeah, just okay. Yeah.
So alphas are usually fractions?
Alphas, yeah. So usually you use fractions, yes, between 0. Yes, exactly. So alpha shouldn't be greater than 1 because it will pass the global best. Agree. You're right. I think alphas should sum to 1. The alpha 1 and plus alpha 2. If you do that, then the alphas will be fractions and they will also sum to 1. Why do I say sum to 1? Because you want to say how much the first term is important compared to the second term and the third term. Okay? Agree? So, yes.
Yeah, so for this example, you have set up and you found the global best and the local best for these x1, x2, x3.
Yes.
So how would exactly the particle swarm start off? You don't know those just yet. Do we just do some sort of neighborhood like local search, and then we go on to the like just velocity thing?
Because initially I initialize the particles, the locations of particles randomly. Then in the next iteration, the local best and global best is obvious, right? In this iteration, for the start of the first iteration, they are initialized randomly. There's no update. No. In this iteration, in the first iteration, then they do local search each. Then the local best and global best are found. Then I can update for the next iteration.
First iteration, like these vectors don't really mean anything essentially, and then once you go to the next one, then they start affecting kind of which way.
You mean before iteration 1?
Yeah.
Before iteration 1, we don't have any update. They are initialized random. Understood? Okay. So now I have 3 vectors. A linear combination of these, for example, is this with some weights. So for example, x1 will be moved toward around here and then do another local search. So the particles are moved. Now, by the way, in your tutorial session, I don't know if you have seen, we showed you some codes for local search, iterative local search, and simulated annealing. So now, assume you want to do particle swarm optimization, visualize it. What should you do? So yeah, so of course, first off, in our local search, we showed you the landscape and the optimization path, right? Do you remember the optimization trajectory? Didn't you watch the tutorial session? If not, that's fine. Go and watch it. So you have the optimization landscape. We showed you this is the candidate solution, and it gradually moves toward the local best, right? This is what we do. Here, when you want to visualize PSO, you should show that. You should also show the particles as dots in this optimization landscape, right? You can also display their local best, their global best. You can iteratively show how the particles are changing. Of course, initially the particles, assume, for example, you have some optimization landscape complicated, doesn't matter. Initially, the particles are random. Gradually, they are moving toward the global best. They convert all of them, because by this update tool, gradually they find the global best. The more particles you have, what happens? The more accurate your optimization solution will be. Because you have more power, but the worse the time complexity. So there is a trade-off. Do you want to use resource? The more resource you use, the more accurate you might get. Don't look at these simple benchmarks that we are showing you. The optimization landscape might be very vast, big, and complicated, such as optimizing the aerodynamics of a plane. So it's not just a small range between -100 and 100 some. It might be high dimensions. High dimensions also vast. So you have a lot of options, regions in the optimization landscape to go. Of course, you need a lot of particles. But the more particles you have for each of them, do you see the time complexity of particle swarm optimization is not that much good? Because you have nested loop. You have a loop for iterations. You have a loop for local search. Also, you have a loop for particles. So iterations, particles, local search. You have iterations. Inside iterations, you have a lot of particles, a for particles, a loop for particles. And for every particle, you have locals. You understood? Okay. So flowchart. In meteoristic optimization landscape, if you see their papers, they usually give you a pseudocode. They also usually draw some flowcharts. Okay, this is how they usually do it. It's a convention. So flowchart is this. Is there anyone here who doesn't know what flowchart is? I can explain. So this is flowchart. So flowchart, so we usually have rectangles, but whenever we want to decide for true or false, to do something or not, we have diamond. Okay, so for example, we initialize the particles, then we calculate the fitness or the cost, right? Then we do the local search for each particle. Then we move the particles according to the update rule. Then we check the termination condition. For example, one of the termination conditions might be maximum number of iterations, reaching maximum number of iterations. We don't want to search more than 1,000 times. Or another way to do that, so you might have several termination criteria. Can you tell me, for example, one of them is maximum number of iterations. Can you tell me suggestions? What? Say it. Do not need to raise hands. Say
like if all the particles end up in the same spot or like around the same area.
So yeah, when the particles have converged, you are saying.
Yeah.
Yes. But somewhat, again, these are variants that you can design. Someone might say, rather than terminating, initialize them randomly again for doing another search. Maybe you got stuck in a local minimum. So again, variants of PSO. So you were saying. Okay, so yeah, so we have these, or you might say my global best hasn't changed for a long time, right? I have searched a lot, but for my last 100 iterations, my global search, for example, global best hasn't changed, or it has changed very small. These things, these can be different termination criteria that you can use. Doesn't matter. I think it's obvious. Okay, and if it's not terminated, do the fitness calculation again, and do the local search again, move particles again, and do the next iteration. So this is the outer loop for iterations. Otherwise, give X with the best fitness. By the way, as also mentioned in the tutorial session, so for storing and returning the best solution in coding, you can do either append to the solutions, right? The best solutions of iterations, you append them, and then you return the best solution. How? For example, you append the best costs that you found in each iteration, the best cost, the minimum cost. Finally, you do an argmin in Python. arguments of cost, minimum cost. Then you return its x. We call it x star. Okay. Someone might do that. Did you understand what I'm saying? So you have a list of best costs. Each iteration has some cost, has some best cost. You append them, and then you can find which one is the best cost, global best, and then you return its x star. Or inside each loop, you can do what? You can always compare your current best in the current iteration with the best so far. So you don't store a list. You always have one variable best solution. You always compare to that, and at the end you return it. Which one is better in terms of complexity? The second one. The second one, of course, the first one, especially if you have too many iterations, is awful for space complexity. Right? Also, for argmin at the end, you need to have kind of like sorting, right? So, but in order not to sort at the end, also not to store a list of the solutions, we can simply have best solution and always update that best solution. Always compare your cost with the best solution. Yes.
Fitness calculation, do local search, then do particles. The way I'm thinking about it was like the treasure hunting analogy is you would be searching first, and then once you find something, then you do the fitness calculation, right? So why is fitness calculation? Maybe I'm misinterpreting what fitness calculation is referring to, but
just give me. I understood what you're saying. Let me think. I think you're right. It's better for them to be one block. Because when you are doing the local search, in each local search, you do the fitness calculation. And then you return the best of each particle. Yes, thank you. But yes, so this is a better flow chart. That what I mean is that in each iteration, every particle should do the local search and return its best solution, and then you compare the best solutions and move the particles accordingly. Thank you for correcting me. Okay, so did you understand my last remark that I said? So it's better to always compare. If my current cost is better than best cost so far, then best cost gets updated by my current cost. So of course you have to update two things: best cost and best best arg cost, argmin. So best mean of cost and argmin of cost. You have to store both of them. Agreed? Don't understand? So why do you need to store best cost? Because you always want to compare to it. Why do you need to store best x or argmin? Because at the end you want to return it. Understood? And best x. Now, can you tell me why in the tutorial session have why we have stored the list? Although we knew that it's not good for space complexity. Yes. Exactly. So we want to visualize the trajectory for you to see how we are updating the solution. So we stored the list. And as we stored the list, we didn't compare with the best solution. We finally returned the argmin of the list, okay? There is another reason that we might need the list rather than doing the second approach. By the way, this that I'm talking about is not just for PSO, it's for the whole materialistic optimization. If we don't want to, sometimes, even when we don't need to visualize, sometimes we have to store the list of solutions. That's because sometimes we want to store the history, and we want to experience them. I want to repeat our bad experiences. Exactly what as we do in life, real world life. I did something awful in my life first. I don't want to do it again. Assume in my meteoristic optimization, I have some optimization landscape. I went in that direction. But I found out that there is nothing there. It's awful there, optimization landscape. It's going up. So I have to store this, not to go back there again, by chance or whatever. Okay, so this is the main idea behind taboo search. Taboo search, we will see that, is a meteoristic optimization algorithm, one of the important ones. As I said, the important optimization algorithms, meteoristic optimization algorithms, have some main idea behind them. The main idea behind taboo search is to store the solutions, not to repeat bad choices. Okay? Therefore, it's called taboo search because those are taboo regions. We don't want to go toward them. Okay? So we'll see that. Acknowledgement, some slides of this slide deck are inspired by teachings of Professor Said Sharifian at Emory University. And a good web link about PSO, take a look at this. That's a good web link. And also it has implemented PSO in Python. And these are the references. Let's have a break and come back at 8:25. Okay, thank you. Okay, so before we continue, someone asked me in the break that can we make PSO parallel using parallel programming? I said yes. So iterations of meteoristic optimization can't be parallel, but in each iteration for the particles, we can do the local searches of the particles in parallel, right? If you have GPU in your system, then the particles, when they are searching locally, they don't depend on each other. So you can do the local searches of particles in parallel, and then you combine their solutions. Then you move the particles. You go to the next iteration again. Then you can do the local searches of particles in parallel. For that, you need parallel programming. I think if you have passed any course on parallel programming, you know that you do a part of the code in parallel, then you combine the results, you do the serial operations, and then you go do the parallel part of the code again. Okay, so if you have GPU on your machine, then of course you can do the particle operations in parallel. That's one thing. By the way, also Piazza has only 80 something students enrolled in it. We have 110 students in the course. Please enroll in Piazza if you haven't. I don't know why people haven't completely enrolled in Piazza. Also, please watch the tutorial sessions as well. So, and you can feel free to ask any questions you have also in Piazza. So let's continue with the genetic algorithm. That's another meteoristic optimization algorithm, and that's very cool, actually. Okay. So let's talk about evolution, natural selection, and Darwinism a little bit. I think you have heard of this, so I don't need to explain too much. Biology and geology, they both have shown that living beings evolve during long-term periods. It's long-term periods, over millions of years, or even sometimes billions of years, okay? They evolve, they change, they try to adapt to the environment. Does adaptation to the environment mean that they get better? No, not necessarily. They just adapt to the environment. For example, human, we have evolved and we have adapted to the environment in the world. Are we perfect? Of course not. We have a lot of flaws in our bodies, in our minds. For example, a flaw in our body is what? Having the two ways next to each other. So I don't know the words in English very well here. So we have one way for in our throat for food and one way for breathing, right? They're next to each other. It is very vulnerable for choking. Right? Why should they be close to each other? Many people die because of this flaw of human's body. They choke. The food goes in the wrong tube. Okay, that's one problem. We have a lot of problems in our minds too. Actually, schizophrenia can be explained by evolution. So, for example, have you heard of horses for racing horses? What do? They make them in a way that their legs become very lengthy, very narrow. When this happens, the horse can run much faster. Okay, so they have done that on the horses. Okay, they mate, they have children. This happens over and over generations, but sometimes the race horses, their legs completely break because it becomes too narrow. Okay. The schizophrenia in humans is because of the similar situation. In our minds, we have evolved in a way that we can understand each other. Right? I can see you, I can talk to you. I can understand you, I can feel you. When you feel pain, I can feel that pain. But when you're sad, I feel that sadness. When you're happy, I feel that happiness. But sometimes, for some humans, because of some mutations, also some evolutions, this becomes too much. This ability of mine becomes too much that they feel and understand some non-existent humans. I talk to a human which doesn't exist because this feature of my mind has become too much, has been exaggerated. This is called schizophrenia. Right? So, as I said, it doesn't mean evolution, doesn't mean getting better, it means adaptation. Okay. So, according to natural selection, every generation tries to adapt better to the environment compared to the previous generation. And I think that's true in various ways. Okay. And why do we call it natural selection? Because nature selects the creatures, the living beings, which adapt better to that environment, right? And therefore, the other living beings will die, right? And they will not be repeated in the next generation because they die. They don't have even a chance to mate and have offspring. So, one of the first people who found this out, there were at least two, but one of them was Darwin, right? That's why it's also called Darwinism. And genetic algorithm, as it is obvious from its name, it is based on evolution and genetic evolution and natural selection. So the idea of natural selection is that mechanistic optimization, that's called genetic algorithm. It was proposed by John H. Holland in 1975. As you see, it's an old algorithm. It is inspired by natural selection and Darwinism. It is one of the evolutionary algorithms. So evolutionary algorithms is also a field of a lot of different algorithms. Actually, if you know archive, right? One of the categories of archive is evolutionary computing, right? So it's a big thing that it has become a category of archive preprints. Okay, so evolutionary algorithms. As another example for evolution is this giraffes. So giraffes, initially they conjecture that they had a small necks but their necks grew gradually to become longer. Why? Because some of the giraffes had longer necks and they could survive because they could eat the leaves on the trees better. But the ones which had shorter necks, they died because they didn't have enough food. They couldn't reach the leaves at the top of the tree, therefore they died. But the ones which remained mated and had offspring. Therefore, these characteristic of having long necks remained in the generations of giraffes. That's the reason. Okay. So we talked about this. Now let's talk about genetic algorithm, cost and optimization variables. Chromosomes. Okay. And this name is obvious, so we are working with genomes and genetics, right? So our candidate solutions now, we call them chromosomes. Okay. You can call it anything. So these in different algorithms, they are naming different, it's the same thing with different names. For example, in particle swarm optimization, they name particles as particles, right? Maybe in gray wolf optimizer, they name the particles gray wolves. In genetic algorithm, they name the particles or the candidate solutions, they name them chromosomes. And the feature, so as you know, every chromosome is a vector, right? It's an optimization variable, right? Or vector or matrix, whatever. So the vectors, the chromosomes have some genes. Therefore, you can consider the features of chromosomes as genes, and every chromosome has D genes if my optimization variable is D-dimensional vector. Okay. So now, possible ways to create or encode the chromosomes. Now I need to have the chromosomes. Either, for example, there are several ways to make the chromosomes. Consider, assume my optimization variable is a D-dimensional vector and with float values, right? For example, it can be any continuous values for the features, right? Then I can consider that D-dimensional vector as a chromosome with D genes. That's one way. So that's exactly how it is. Another way is that assume my optimization variable is a scalar, float a scalar, right? Sorry, integer scalar. Do you agree that I can convert it to binary string? Right? So I can have binary string. This one, either in two cases, at least I can, in my mind, in two cases, you can have binary chromosomes. Either you have a scalar optimization variable and you convert it to binary, or your optimization variable is actually a binary vector. For example, you have some features you want to see whether they should exist or not, right? The features might be binary actually. Or you might have order. What do I mean? So you have some things, and one order of these things is the optimal order. You can think of a lot of applications for this, right? Agree? So if in industry, you have several things, and you want to order them. So you give some index to each of them. 0, 1, 2, 3, 4, 5. Which order is the best order for my task? So your task determines the cost or the fitness, right? So for your task, which order is better? Therefore, every permutation can be a candidate solution, right? So I have different ways to make chromosomes. The fitness or cost function value is the evaluation of function at a candidate solution. We know that. Okay, I think that was obvious, but to recap, okay. So which is a D-dimensional chromosome, and at that, I have some fitness or cost function. Usually in genetic algorithm, we want to maximize the fitness function. Okay, yes, we usually maximize. In general, we either maximize the fitness function or minimize the cost function, and we know how to convert with them to each other, right? When you have a minimization, we talked about it in preliminaries. You can convert it to maximization and vice versa. In genetic algorithm, we usually maximize a fitness function. or equivalently maximize the negative cost. Therefore, if I have a cost, minimization of a cost, I can convert it to maximization of a minus cost. So I can consider minus cost as a fitness function. Okay. Fitness or cost calculation. So at every iteration in the genetic algorithm, we calculate the fitness or cost of chromosomes to see how good they are. You agree? Every chromosome is some point in this optimization landscape. It has some cost. So I can evaluate the cost of every chromosome or every particle, whatever you want to call it. Now, let's see the natural selection in genetic algorithm. As I said, it's based on natural selection and evolution. Okay. Natural selection. So what is that? Who remains to be parents of the next generation? This is natural selection, right? Some particles, some chromosomes die because they were not good or they were not adapting to the environment. Some remain and they become the parents of the next generation, right? This is natural selection. So at every iteration, we select some of the chromosomes from the current generation to be the parents of the next generation, and the others will die. Okay. The other chromosomes which are not selected will die without having offspring or children. Offspring is another name for children. So offspring of this generation will be candidate parents for the next generation. Because you know that some of the offsprings will not be good and will die. Some of them will be parents of the next generation. Good? Okay. There is something named selective pressure in this algorithm. It's also called takeover pressure. So what does it do? The more the selective pressure is, the more the speed of selecting the elites as parents. What do I mean? If you are very idealist, you say in your natural selection, you can be an idealist or you can accept not very good parents too, right? If you're too idealist, you say only the best parents and the rest must die, then you mean that your selective pressure is high. What happens if my selective pressure is high? If I'm too idealist, what happens? What? So can you say loudly? I can't hear. You don't explore. Exactly. You get stuck in your local best. Why? Because you're saying that these parents are the best. But these parents, what if these parents are in the local best? Maybe one bad candidate is close to the global best, but it is close to the global best. It's not global best. It is still bad, but if it searches more, it can find the global best. But you killed blacks in this situation, right? So this selection pressure says how much should I explore versus exploit. Of course, you might say, okay, so in my genetic algorithm, initially I can have low selective pressure to explore more. Gradually, I can increase my selective pressure and I become more idealist because at the end, I need to exploit more, right? Okay. There are various ways for natural selection of chromosomes to be parents of the next generation. What are they? Random selection. So we are reviewing some different methods to do natural selection. By the way, it has several stages. Every stage has several ways to do that. So you have a lot of combination of variants of genetic algorithm. Okay. So random selection was one of them. What does it mean? Select K random chromosomes as parents. Even don't care about their fitness, cost. Randomly select K parents. Of course, its selective pressure is very low. You're not selective at all. It's just randomly selected, right? So it has too much exploration. Not even good, maybe. Too much exploration. One of them is elitism selection. So you only get the elites of the generation. You select the top K chromosomes. You select the top K chromosomes with the best fitness or cost values. But as I said, it has the risk of getting stuck in local optimum because it has too much exploitation. So these are the two sides of exaggeration. Either I am completely random, I am completely idealist, and I get only elites. Now we have middle case scenarios as well. One middle case scenario is this: proportional selection. What do? For every chromosome, we calculate a probability of being good or compatible with the environment or having good fitness value, right? How much it adapts to the environment. So this is the probability. And what is that? It's fitness, Fi, over summation of Fi. So I have a bunch of fitnesses, right? But I want them to behave like probability. I told you the technique was dividing them by sum of them, right? So I divide each fitness. So assume I have n chromosomes, so I have n fitnesses. So I divide each fitness by the summation of fitnesses, and they become between 0 and 1, and they sum once they behave like a, of course, the more the fitness, the more the probability. That's why I said usually in genetic algorithm we want to maximize the fitness, okay? And it makes sense because the better the chromosome, the more probable I should be to take that as a parent. Okay. Then, so every chromosome has its probability for being selected. If I sort the probabilities from largest to smallest, it becomes elite idealist, right? If I only take the best probability, it becomes elitism method, right? Selection. However, I don't do that. I make it stochastic. So I choose by probability. Okay, let me explain this, and I will go back to the previous slide again. So how can I use the probabilities? I have a bunch of n probabilities for n chromosomes. There is a technique in computer programming, specifically for materialistic optimization, and that's called roulette wheel. It's exactly as a roulette wheel in casinos. Have you gone to Las Vegas? So you might have seen roulette wheels. So you have roulette wheels, and then they say, okay, they bet on some specific colors, and they rotate the roulette wheel. So this is how we use that. We use the idea of roulette wheel in our computer program for selection. How? You agree that the probabilities should sum to 1, right? Therefore, I can consider them as parts of a circle, and all of them cover the whole circle or the whole roulette. Agree? Then I have a pointer. Then I rotate this roulette with some random speed or random number of iterations. Doesn't matter. Then wherever it stops, the cell in front of the pointer, we may select it as a parent. Okay. I do this again and again and again for several times, so I select all of my parents. Okay. Of course, if a chromosome has higher probability, the more probable it is to be selected by the pointer. Agree? Now, by the way, you might be wondering, what if for the next time I select the same parent? You ignore that. Rotate it again. Rotate the roulette wheel again and again until you find another parent. Because you want to find k parents, right? Do it several times until you find your k different parents. Okay. Now, this was the idea of roulette wheel. How can we code it? In Python, in MATLAB, whatever. How can we code it? Simple. What? Say array. Maybe you can use array, but a simpler idea is this. Consider the range between 0 and 1. You open this roulette wheel to become like a line between 0 and 1. Then the more probable, so they sum to 1. The more probable a chromosome, the more range it takes in the range between 0 and 1, right? So, and the order doesn't matter much. The order doesn't matter because they sum to 1, and the more probable has more chance. Then you generate a uniform random number between 0 and 1. It gives you the pointer. Where does it fall? Then you select that. Did you understand how we implemented solid wheel in programming language? Okay, interesting. We can have a stochastic universal sampling, or SUS. What is it? Do you remember I told you what if I select the same parent again and again? One way to resolve that issue is to have several pointers, right? Then I rotate it. Then one of the pointers will face some region, one of the pointers will face another region. Also, it has another reason for why we want to have several pointers. Because if we have several pointers, we give some chance even to chromosomes with less probability. Only having only one pointer exaggerates for selection of the elites. If I have several pointers, it gives a chance, it becomes more democratic, right? It gives more chance to people who have less chance, right? That's it. Okay. By the way, one might say, I don't want to use equation 1. Rather, I want you to use equation 2. So the difference is minus F mean in the numerator. What does it do? So F, the fitness is, take the minimum fitness and subtract the minimum fitness from the numerator. Why can't we do that? What's the philosophy? Because this exaggerates the probabilities. If something has more probability, it will be exaggerated. Sometimes maybe you want to have more selective pressure, so you do that. Okay. For making the differences of probabilities bolder. Okay. Have you noticed one important thing in either these, especially equation 1? What if some of my fitnesses are negative? Some of them are positive. Then this will be awful, right? This formula. Okay, we will shift them. We'll shift all of them to become non-negative, right? We can add all of them to the absolute value of minimum, F mean, and then use equation 1. Agree? Okay. Bye.
The second equation, how does subtracting minimum fitness exaggerate the confidence?
Because, well, so the question is why equation 2 exaggerates the selective pressure. Because consider the chromosome with F mean, with minimum fitness. Its equation 2 becomes 0. Its probability becomes 0. So you are completely removing it. You are completely removing the worst chromosome in this generation. But equation 1 gives it some chance. You understand? Okay. So another way to do natural selection is rank-based selection. So what do you do? It's close to the termination, close to the end of the algorithm. So the more iterations that you have gone, the probabilities in the roulette wheel with probabilities will become very close to each other. Do you agree? Do you agree with that? Because initially chromosomes are sparse, but they gradually converge to each other, right? Because they are getting adapted to the environment, so they become similar to each other. The races will mix, they become more similar to each other. Okay, so it will be better, so the probabilities will be the same. Then what happens to the roulette wheel? It becomes something like this. there with a lot of small probabilities. Sorry, I couldn't draw very well. With a lot of small slices, right? Then what do? So it will be better in this case to rank the chromosomes, rank them by their fitness values in the late iterations. In initial iterations, the simple roulette wheel is good. But in the later iterations, we might change it to the rank-based roulette wheel. How do we do that? So we say we calculate the fitnesses, assume my third chromosome has the best fitness. Then my first chromosome, then my fourth one, then my second one. Assume. Yeah. In each generation, I calculate the fitness for each chromosome. Okay. Then I'm ranking them. Note that. Assume I have n chromosomes in this generation, but I only take k parents, where k is much less than n or less than n. I don't take all of them as the parents. Otherwise, I don't have any natural selection. Okay, so, but usually we set the number of children to be n again, because we don't want to decrease the number of population. Okay, so what we're seeing, so I rank the chromosomes and then I calculate the probabilities in this way. So I use that formula for making it behave like a probability on the ranks. So the first one has the 4 scores. Over 1 plus 2 plus 3 plus 4. The second one has the third score, 3 scores. The third one has 2 scores. The last one has 1 score. Here because I have 4 chromosomes. Did you understand? In this way, just let me finish. In this way, no, that's fine. In this way, what happens? Although their fitnesses are very close to each other, but they have different probabilities. So what here, for example, what do I mean by very close to? Here, for example, its fitness is 1.01. The second one is 1. The third one is 0.9. The fourth one is 0.8. They're very close to each other in terms of fitness, but still they have rank. Okay, what was your question?
Try to increase some people's probabilities, like try to exaggerate the difference because we want to start to exploit more.
So no, the thing is that at the late iterations, the philosophy of roulette wheel will be questioned because all of them will have the same probability. Then why do you do roulette wheel? You randomly select. Because if you don't do that, the simple roulette wheel in the late iterations converges to random selection. Right? You don't want to do random selection. That's right. You have a question? Ask me if you didn't understand.
You're okay.
No, that's fine. You understood? Okay.
One question.
Yeah.
So with every iteration, you can have more chromosomes created?
No, so at every iteration, we select a subset of chromosomes as parents. Then we generate children with the same population as the previous population. Yes.
If at like close to determination, all the fitness values are really close to each other, they're almost the same.
Yes.
Why would it matter? Wouldn't it be okay to just do random selection and all the fitness values are like, since they're pretty close to each other?
Yes, you might say in late iterations, as the fitnesses are very close to each other, well, it doesn't matter, take them randomly. But I'm saying that still we don't want to do random selection. We want to give chance to better solutions, but more. Yeah, kind of. Yes. Another way is tournament selection. And what is that? It says that let's group the chromosomes randomly and then do random selection from the chromosomes. It is in statistics, it's called stratified sampling. Have you heard of that? So, for example, we have various ways to do sampling, such as simple random sampling. One of them is a stratified sampling. So stratified sampling, it says make groups or clusters, or they call it strata or groups of the data, and then from the groups randomly select. This is called the stratified sampling. This is good for reducing the variance of estimation. For more information on sampling techniques, you, feel free to take a look at my tutorial named survey sampling algorithms from survey sampling to Monte Carlo methods tutorial and literature review. It's available on archive. Okay, you can take a look at it. So here, this is tournament selection. A special case of this is that we get these, we rank them, and then we get top K. You can see it as a special case also. These are different variants of natural selection. So natural selection is over. Now we go to crossover. So what is that? Crossover is another name for mating. Okay, two chromosomes mates to generate offspring. Okay. So crossover, mating of parent chromosomes to generate offspring or children. It is used for exploration. Why? I have two parents. They make a child. The child is a new person and searches for itself. So I jump to different parts, and this is good for exploration. There can be crossover either with either two or multiple parents. So I can have either two parents for one child or multiple parents for one child. There are various variants for the genetic algorithm. Okay. From every two or more than two parents, we can generate either only one or multiple offsprings. Okay. Every two parents or every several parents can have either one offspring or several offsprings, doesn't matter. Again, we usually set these parameters in a way that we don't want to reduce the number of population. Okay. There again, various ways to do crossover. One of them is 1 point crossover. What does it do? Consider these two chromosomes. Randomly take one of so for example, between features, I have several options. I can either take here or here or here or here, right? When I have 1, 2, 3, 4, 5 features, I have 4 options to take, to select. When I have D features, I have D minus 1 options to take. I select one of them randomly, such as this one, okay? Then I break each parent from that part, okay? So each parent is here, is broken into left and right parts from that part. Then I take the left part of one parent and concatenate it with the right part of the other parent. This becomes a new child. And you see, I did it in 1 point, therefore it's 1 point crossover. As a cartoon, assume there are two humans, you make a half of a human from the one parent, maybe head to hip from one parent, hip to leg from another parent. You concatenate them, it becomes a new human, okay? So as you see, we can have two children. Why? Because taking the left of parent 1 with the right of parent 2 becomes child 1, or the other way around, taking the left of parent 2 and concatenate it to the right of parents 1 becomes child 2. Here, my chromosomes are vectors. If I have matrices, I can cross over in different ways with rows and columns. Agreed? Okay. We can have multi-point crossover. Rather than 1 point, I break them down with, for example, on 2 points or 3 points. Then, for example, I get region 1, region 2, region 3. Region 1 of parent 1, region 2 of parent 2, region 3 of parent 1. It becomes child 1. And the opposite for child 2. Understood? Okay. Uniform crossover. By the way, when I said you have these options for crossover, it doesn't mean that necessarily for a specific algorithm you stick to one of them. In different iterations, you can also randomly select one of these crossovers. In the first iteration, for each offspring, you randomly select one of these crossover algorithm methods. Did you understand what I'm saying? Okay, so another one is uniform crossover. What does it mean? Randomly choose the jth gene from one of the parents. For the jth gene of the offspring, for every feature of the offspring, select that feature from one of the parents randomly. Understood? So you can have a lot. In this way, you can have a lot of offsprings. A lot of offspring. Another one is arithmetic mean crossover. So here, this is especially useful for continuous vectors. Okay, so what do? You have alpha x plus 1 minus alpha x2. So x1 and x2 are the parents. So this is a linear combination between the parents. When you change alpha from between 0 and 1, you will have different linear combinations, right? You can have various offsprings. Two of the offsprings can be alpha x1 plus 1 minus alpha x2 and alpha x2 plus 1 minus alpha x1. So, for example, here, this is an example with alpha 0.3. For each feature, what does it do? For each feature, it does the linear combination. You have a question? Okay, another one is geometric mean crossover. So that was the arithmetic mean, right? Now you can have geometric mean. So one of the parents to the power of alpha times the other parent to the power of minus alpha. And here the parent is a vector to the power of alpha. I mean, every element of that vector becomes to the power of alpha. Okay? And then you multiply them. I agree, these are easy. But when you code them yourself, you'll see the interesting behavior of the algorithm. Now let's make it a bit complicated. This is UNDX, unimodal distribution crossover. Sometimes I put some more complicated things for you not to be bored, okay? So one of them is this. It is multi-parents crossover method. So you should have it for this 3 or more parents. What do? We fit a unimodal Gaussian distribution with mean mu and covariance sigma to the m parents. Assume you have m parents. Do you agree that you can fit some Gaussian distribution to them? How? If I'm considering only unimodal Gaussian distribution, I can use these formulas. These formulas have been found by maximum likelihood estimation, for example. If you don't know what that is, doesn't matter. These are the formulas. So this is the mean of the distribution. This is the covariance of the distribution. So we are approximating the mean of Gaussian by average, as equation 8, and approximating the covariance by sample covariance. This is sample covariance. Okay? Do you understand what I'm doing? Okay. Then what happens? Then we sample as many offsprings as desired from this Gaussian distribution. So it has a Gaussian distribution. Now we fit that. Now it becomes a probability. Now you can sample from this probability distribution. Right? An example is this. For example, dimensionality is 1. It means that points are scalar. So assume I have 3 parents, 3 scalar parents. I can fit a Gaussian distribution to them like this. Then I select the sampled offspring. Or if D is 2, then I'm looking to it from above. Then I fit a Gaussian distribution to it. Then I sample from it. For example, here, sampled offspring is here. Agree? By the way, of course, the more samples you have, the better the Gaussian distribution is. If you do it in practice with 3 points, you can't fit a good Gaussian distribution. You need at least 10 points, I believe. So this method might be good if you have 10 parents per offspring. Okay. You can have PCX, parent-centric crossover. This is more complicated. What is it? Rather than fitting a unimodal Gaussian distribution, let's fit a multimodal Gaussian distribution, a mixture of Gaussian distributions. Have you heard of Gaussian mixture model or GMM? It simply is like this. Consider these 3 points. If I fit a unimodal Gaussian, it becomes like this, right? But if I fit a mixture of several Gaussians, then it will give me several modes, right? Where the integral under this probability distribution is 1. Okay? Then I sample from this. This is more accurate than fitting 1 point, right? For more information, by the way, for more information on fitting mixture distributions using expectation maximization, refer to our tutorial. This is optional. Don't freak out if you don't understand, but feel free to read it, optional, and ask me if you have any questions. If you are coding, you don't need to implement GMM yourself. There is library for it in scikit-learn. Okay. Another technique is SPX or simplex crossover. You know what is simplex in mathematics? So you can see simplex as a generalization of triangle to higher dimensions. So in 2D, this is triangle, right? In 3D, it becomes a pyramid. In 4D, you need to imagine it. We call all of these simplex. Simplex in 2D, simplex in 3D, simplex in 4D. Agree? So in simplex, we have planes intersecting each other. Okay. So like this. Now, do you agree that assume I consider the parents as the vertices of the simplex? Then I can sample the offsprings from inside the simplex. For example, a triangle, I can sample from the inside the triangle. Or a pyramid, I can sample the offsprings from inside the pyramid. As you see, it becomes some kind of the offspring as expected becomes a kind of a linear combination of the parents. Mutation. So random changes to the offsprings after crossover. After I have the generation, the offsprings, then sometimes each of them change a little bit. This is exactly what we have in evolution. For example, 2 parents have a child. Suddenly that child has for example, 2 parents, they don't know anything about music. They hate music. They have a child, the child suddenly becomes Mozart. That child has some mutation. That child didn't get that characteristic from the parents. Okay? So this is good for exploitation. Why? Because every point changes a little bit to do something like local search. So the local search in genetic algorithm is implemented by mutation. Right? We don't have any local search. Usually the chromosome does a mutation. Okay, so it goes to its neighbor, something like that. We have various ways to do mutation. One of them is uniform mutation. What does it do? It says generate some random probability between 0 and 1. You know how to do it in Python, right? Uniform random values between 0 and 1 for the features. Then for the top k genes with highest probabilities, we change the genes values to random values in the range of that feature. In simple words, randomly select the features, some features, maybe one feature, maybe several features, and change their values to some value acceptable in the domain of that feature. You shouldn't go outside of the domain, right? Assume that feature is always between 0 and 1. Can I change that value to 2, to 3? No, because it must be between 0 and 1. So change it to some acceptable value. Okay? Randomly change some features. Another thing is bit flip mutation. Assume it's good for binary chromosomes. You select some of the features and you flip them. If they are 0, they become 1. If they are 1, they become 0. Another one is swap mutation. Randomly take 2 features and swap them. Do you understand the differences? So there is no parent here. There is one chromosome, and we're changing that. A scramble mutation. Get a part of the features, then scramble them, the order. Okay. Another one is inversion mutation. Get a part of the features and invert them, their order. Macro mutation or headless chicken. What does it do? So it says this mutation is implemented as a crossover of the chromosome and a random chromosome. So you take the chromosome, you generate a random chromosome, then cross over this chromosome with that random chromosome. Did you understand? So like this is X, this is a random solution. Then I use a 2-point crossover on them. This is a mutate. Okay. The flow chart of genetic algorithm is this. So first off, with termination criteria, we have various things such as reaching maximum number of iterations or reaching maximum elapsed time, right? I don't want to optimize over 1 hour, for example. Reaching a small enough cost or large enough fitness compared to a known threshold. Sometimes you know that your cost can't go below, for example, 5, right? So if you become 5 point, the best, your local best becomes 5.01, they say it's good enough. Or other termination criteria. There are a lot of them. Okay. So this is the flow chart. Initialize the chromosomes randomly. Then when I say randomly in the domain, right? In the feasibility set, randomly in the feasibility set. Then do the fitness calculation at every chromosome. So again, there are different variants. Usually the original genetic algorithm, every chromosome doesn't do any local search. Every chromosome calculates its fitness at the same place it is. Okay. The local search is carried over by mutation. Okay. But there might be some variants of genetic algorithm which also borrow the idea of local search. So every chromosome also does the locals. So you can have a combination of algorithms. Agreed? Okay, so you do the fitness calculation, then you do the natural selection for the parents. Then the selected parents cross over, they will have children. Then the offspring or children, they have random mutation. Not all of them. You can have you can also do it randomly. And for every chromosome, generate a random value between 0 and 1. If it is less than 0.5, mutate it. If not, don't mutate it, right? Do some random mutation on some of them or on all of them, then check the termination criteria. If not, go to the next iteration. If yes, return the best solution. Okay. By the way, you also understood that the crossover and the mutations had different variants, and some of them had different hyperparameters. So these are chosen by user, right? Okay. Acknowledgement. Some slides are inspired by teachings of Professor Said Sharifian. This is a good web link about genetic algorithm. There are surveys on genetic algorithm variants. There are a lot of them. And these are the references. Your question? Can you say loudly? Yeah. How do we optimize our optimization algorithm, right? So for different optimization algorithms, we know that, for example, this optimization algorithm has some flaws. So we know flaws and the benefits of different algorithms. For example, I can tell you that genetic algorithm its flaw is that it's prone to get stuck to the local optimum. I have run it several times. By experience, you can find out their flaws. If you run genetic algorithm, you will see that especially for very complicated cost functions, if you use the original genetic algorithms without any local search and these things, they might get stuck in the local base. For example, in terms of not getting stuck in the local base, PSO is better. So this is for choosing the optimization algorithms. And also, some optimization algorithms are good for some specific tasks. For example, if you, as I said, if you have a graph, maybe ant colony is better, right? So that's another way to choose the optimization algorithms. Now, going inside the guys, please listen, start over it. So going inside the optimization algorithm, now how do we choose a variance? Maybe by trial and error, or maybe by knowing some prior knowledge about your problem, your optimization problem, about your task. Sometimes some variant needs a lot of computation, but your embedded system doesn't allow that. So these are different ways to choose. I'm giving you freedom. I agree that. I don't know if you have heard of this. In existential philosophy, they say that one of the concerns of human is freedom. Why? Because freedom gives you responsibility, brings you responsibility. Therefore, people usually are afraid of too much freedom. As a result, you can see that in algorithms too. When your algorithm has too much freedom, it's a flaw for that algorithm. Because you don't want to give too much freedom to the user to choose the variance. The user is lazy and they say, do it yourself. I don't want to optimize. I agree. So, but there are freedom, there is freedom, there are a lot of variants, you should choose that. And it brings you responsibility. And that is an existential problem. Okay, any question? Yeah. Guys, please.
Should only happen within a certain range of a feature. What's the feature mean?
Yeah.
What is feature?
So the dimensional is a vector, right?
It's this.
Well, it's almost
Like 500.
So one of the targets was the dominant part.
Yeah,
Let me stop this.